All right, good morning. All right, so we got a lot to cover, so let's just go over this stuff. All right, so net force deals with multiple forces. According to Newton's second law, what causes the net force? What causes acceleration is the net force. All right, if something is speeding up, slowing down, or changing direction, it's speeding up, slowing down, or changing direction. Hey, Ziggy, get away. Speeding up, slowing down, or changing direction because of the net force. So the question is, what is a net force? Real life kind of like this. Look, there's a push in this direction. Gravity is pulling it down, so it's got weight. R is a retarding force. Its motion is being retarded or resisted. So when you got all these forces all over the place, what's the meaning of the net force? So that's what we'll be dealing with in essence.
Chopping down a tree clean through by steps.
All right, so a tree is being pulled in this direction, and the roots will pull the tree in the opposite direction. So if that's the case, what's the net force that you're looking at, right? So you got two forces acting on this mass. There's a 25-pound pull in this direction. There's a 20-pound pull in the forward direction. So what's the net force? So the net force is the sum total of all forces. So which means that we will have to sum up all the forces acting on the system. All right, so when we say sum them up, it doesn't necessarily mean that you're just taking 20 and adding 25 to it. That's not how things are summed up. Direction is going to matter. To the right, you can make positive. To the left, it's going to be negative. And you know at the end, it's going to be 5 pounds, right? From your own life experiences, you know that if there's a pull here and pull in the opposite direction, you kind of have to subtract things from each other. All right, so the net force is the summation of all forces acting on the system. This means summation of all the forces acting on the system. So the net force is going to be responsible for the acceleration of the system that you're looking at. And the net force is, you're summing up the forces. F1 is to the right, so it's going to be positive. F2 is to the left, so it's going to be negative. So it's going to give you a net force of 5 pounds. So this 5 pounds is going to be responsible for the acceleration of the system that you're looking at.
At the same time,
the net forces.
RPMs. Barbara watches, terrified and helpless.
What's the net force acting on the sky? All right, and most of you guys usually say it's 0, which is correct. And when forced to explain, you go, oh, airplanes are moving at the same speed. Guys, airplanes are not moving. Are you kidding? They're not moving. So what makes you think that the net force acting on them is 0? All right. I mean, there are a tremendous amount of forces acting on this guy. If I were to take this guy's place, I could easily lose my arms. All right, there are a tremendous amount of forces acting on this guy. So how is it that the net force is 0? The net force is 0 because you got to go back to the definition of acceleration. You have to go back to the definition of a force. What does a force do? Force causes acceleration, right? So you know that the acceleration is 0. As a result, the net force is 0. That's it.
All his physical and mental strength, both engines are physical and overpowered. But somehow, then suddenly,
right now, the net force is 0. Now it's not, because now he accelerates.
He's pulled off balance.
If he's accelerating, the net force is not 0. What that means is this airplane is applying a force which is slightly larger than the force applied by the other ones. Weight is a gravitational force acting on you. Force of gravity is known as weight. Is gravity a force? When somebody asks you a question like that, what they mean is, does that fit in with the definition of a force? All right, so force is anything that causes acceleration, right? So the following objects will accelerate under the influence of gravity. So they will accelerate at a rate of g. All right, so which makes gravity a force. All right, so here's the force acting on this object expressed in terms of the gravitational acceleration. So that becomes the subject's weight. So W is going to represent weight, and the object's got weight moving in the downward direction. Except the problem is, what's the acceleration of an object when it's sitting on a tabletop like that? It's not accelerating, right? So it's 0. 0 times mass is going to be 0. So you almost creates the impression that this thing is weightless under the circumstances. Still got weight when you try to lift it up. Obviously, you will feel it. And so why is that the acceleration is 0? It's still got weight, right? The acceleration is 0 and still got weight because the net force acting on it is 0. All right, it's being pushed down in the downward direction by the gravitational force. It's sitting on a tabletop. It's pressed against the tabletop with its weight. In turn, the tabletop applies the same force back on it in the opposite direction. All right, so that's known as the surface force or the normal force. All right, so this thing comes down while it's accelerating at a rate of g, and boom, it's some kind of a surface. The weight is still there. All right, g is still 10. I know g is still 10 because as soon as you remove the surface, it's going to keep accelerating at a rate of 10 meters per second squared. And it stopped accelerating because the net force acting on it is 0. So which means that there's a second force acting on it that equals its weight. It's called normal force. It's not normal. It's not used in the sense of normal versus abnormal. It's known as normal force because it's a mathematical term. Normal means it's something which is perpendicular to a surface. That's what it means. So the force is perpendicular to a surface. You could call it the surface force. In physics, we call it the normal force. So it's a reaction force and any force applied to a surface. It's always going to be 90 degrees to the surface. That's what it means. All right, and let me check to see what we got. All right, that's good enough. Normal force reading from a scale is known as your apparent weight. All right, so known as your apparent weight. It's called apparent weight because of the simple reason that your scale reading may or may not be the same as your actual weight. You can fool the scale into thinking that you are heavier or lighter.
Oh, 225! That means I lost weight!
Homer, you're on the towel rack.
By shifting your weight onto a different surface, you can put 1 foot on the ground, you will weigh less. You put an arm on a countertop, you will weigh less. So you can fool the scale. When the elevator starts to move from rise in the downward direction, you feel heavier, lighter, about the same. All right, guys, you will feel lighter. Is that just the feeling that you get, or is that really what happens inside the elevator? Well, we can figure out, right? Just get a scale, step on it. This guy weighs 240 pounds. As soon as the elevator starts to accelerate in the downward direction, you will feel lighter, right? And then you will become lighter according to the scale. When the elevator is moving at constant speed, no change in weight. When the elevator is going down and slowing down, you will feel heavier because according to the scale, you will become heavier. So the conclusions: no acceleration, no change in weight. Acceleration is downward, you will feel lighter. Acceleration is upward, you will feel heavier. All right, so no acceleration, no change in weight. When the acceleration is pointing upward, you will feel heavier. When the acceleration is pointing downward, you will feel lighter. So the question is why? All right, so here's your weight. That's the force of gravity acting on you. As a result, your acceleration is 10 meters per second squared. All right, your mass is measure of inertia. Your weight is the amount of gravitational force acting on that mass. Normal force is a reaction force. The inner force applied to the surface. It's going to be 90 degrees to the surface. Apparent weight is your normal force reading from a scale. Apparent weight can be different from your actual weight because you can shift your actual weight onto a different surface, and it's also going to be sensitive to acceleration, right? When the elevator starts moving in the downward direction from rest, you will feel lighter. When the elevator is accelerating in the upward direction, you will feel heavier. And when there's no acceleration, there's no change in weight. All right, so a little bit of a math. This is more of a modeling. I'm more interested in the end result of it. All right, scale, your center mass. This is your weight. This is the scale reading, your apparent weight. Acceleration is in the upward direction or downward direction or 0. All right, so we'll sum up the forces on the y direction. N is positive, W is negative. All right, so net force is what causes acceleration. All right, so we'll isolate N by adding W to both sides. All right, so here's a mathematical expression for how much you appear to weigh inside an elevator if you're standing on a scale. So this is your apparent weight reading. So that's your weight reading from a scale. So if the elevator is accelerating in the upward direction, acceleration of your mass is going to be added to your weight, so you will appear heavier. That's what it means. If the elevator is accelerating in the downward direction, acceleration of your mass is going to get subtracted. Acceleration times your mass is going to get subtracted from your weight, so you will feel lighter. Hey. All right, so there's no acceleration. Scale reading is the same as your actual weight. All right, the one that I'm interested in that we will take with us to the next portion is the mind twister. Hey, Ziggy, no. All right, so we got the mind twister. So the scale, as soon as the cable snaps, how much do you appear to weigh? If you're standing on a scale, if you were to look down, what do you see on the scale? All right, so that's the one that we will focus on. All right, so as soon as the cable snaps, the acceleration is in the downward direction, right? And as soon as the cable snaps, the acceleration is going to be the same as the gravitational acceleration. So this A is the same as G. That's what it means. So this A is the same as G. All right, so here's your weight, mg. Here's your mass, accelerating at a rate of g. So mg minus mg is going to be 0. All right, so what does it mean? Which means that you and the elevator are falling at the same rate. Free fall, everything falls at the same rate. What that means is your center mass and the elevator are falling at the same rate. So when you look down, you're not going to be, scale reading is going to be 0. You're not going to be able to feel the scale under your feet. That's what it means. You will feel weightless. So as soon as the cable snaps, the second, the fraction of a second, boom, this snaps, you will feel weightless. All right. As soon as this snaps, you're weightless. You will feel weightless. That's what it means. You won't be able to feel the floor under your feet. You won't be able to feel the floor under your feet. All right, guys, just highlight that. You won't be able to feel the floor under your feet. Your center mass and the elevator will be falling at the same rate. All right, so that's what it means. You will become suspended relative to your center mass. All right, so when the elevator starts to move from rest in the downward direction, acceleration is down. You will feel lighter. Question is why? Answer is because of inertia. You got mass. All right. And your mass is a measure of your inertia. So bigger the mass is, the larger the resistance is going to be to change in motion. All right. Bigger the mass is, the larger the resistance is going to be changing motion. All right. So, and that resistance to change in motion is going to appear as the deficit on the weight scale. If the elevator is moving at constant speed, we're changing weight because of inertia. All right. Because you're maintaining your initial speed. All right. So going back to this, when the elevator starts to move from right in the downward direction, you will feel lighter. All right. When the elevator starts in the downward direction, you will feel lighter because of inertia. Your body is trying to maintain its initial motion. When the elevator starts to move from right in the upward direction, acceleration is in the upward direction. So you will feel heavier because of your inertia. When the elevator is moving at a constant speed, no change in motion, no acceleration. You're maintaining your initial motion, so you will feel the same. When the elevator starts to slow down to stop while moving in the downward direction, do you feel heavier or lighter? About the same. It's slowing down to stop, right? So you will feel heavier because the body is trying to maintain its initial motion. So it's going to resist changing motion. Car versus an SUV, 60 miles per hour, both. They'll lock up their brakes at 60 miles per hour. They will skid to stop. So which one, if any, will come to a stop sooner? All right, so this is one of those observations that could be argued either way. All right, so most will say the car will come to a stop sooner because it's lighter, and some will say the SUV is going to come to a stop sooner because it's heavier. All right, car will come to a stop sooner because it's lighter. It requires less force. SUV is going to come to a stop sooner because it's heavier and experiences more friction. Either way, frictional force is going to bring them to a stop. So who's right? Who's wrong? All right, so that becomes a bit of a mind twist. Now you got two cars, both going at the same speed, initially 60 miles per hour, one with, the other without the anti-lock brake system. So which one will come to a stop sooner? All right, interestingly enough, people still split on this one. I never thought that this would have been a topic of discussion in a physics class. All right, I thought that everyone knew the answer. As it so happens, not so much. 50% of you guys are usually clueless as to which one will come to a stop sooner. The reason is because if you have an anti-lock brake system, it's going to pump the brakes for it. It's interrupted friction. It's intermittent friction. And that's the reason why some people think that you will control the car better, but that car is not going to come to a stop any sooner. All right, so we'll find out. Car versus a train. Both of them are going at 60 miles per hour. Both of them will lock up their brakes at the same time. Which one, if any, will come to a stop sooner? Most of you guys will say car. And if I were to ask you why, you will say because the car is lighter. That's the reason why it's going to come to a stop sooner. Is that the reason why? All right, so according to Newton's second law, what causes acceleration is a net force, right? External force. External force is responsible for it. But whenever we walk, you speed up, slow down, and change direction at will, right? So where does the external force come from if that's the case? You guys are thinking, oh, you get it from your muscles. I'm thinking, no, you don't get it from your muscles. All right, that's muscles generate an internal force, not an external force. External force is a force that has to be external to your mass. It needs to be external to your body. Internal forces will not cause an acceleration. You cannot lift your entire body up by grabbing your nose and pulling it in the opposite direction. Because muscles generate internal forces. So where does the external force come from when we walk? Well, we generate an external force through Newton's third law. You apply a force on the ground in the backward direction. In turn, the ground is going to apply a force back on us in the forward direction. Through friction, you apply a force in the backward direction, and through friction, the ground is going to apply a force back on you in the forward direction. All right. So if it weren't for friction, none of us would be here today. Just get it into your heads. And you know what I'm talking about, right? I'm still talking about walking. All right. None of us could get around without friction. None of us. It would be an impossibility. All right? You could go through the motions, but you're not going to be able to advance or go wherever you want to go. All right. So through friction, you apply a force on the ground in the backward direction. In turn, the ground is going to apply the same force back on us in the forward direction. All right. So having said that, this video is all right. So the cars with the anti-lock brake systems will come to a stop soon. All right. They will come to a stop soon. If you get an anti-lock brake system, not only will you control the car better, also that car is going to come to a stop sooner. The question is why? Because the anti-lock brake systems will generate more friction. That's the reason why. The thing of it, though, it's intermittent friction. All right, it's not one single continuous friction, the sort of friction that you get when you lock up the brakes without the anti-lock brake system. It's intermittent. It just boom, boom, it pumps the brakes for you. How does that generate more friction? So that becomes a mystery for a lot of people. So which means that we have to take a look at the nature of friction in order to solve this puzzle. All right, so nature of surface friction is, you can argue that the size is going to matter, the surface area content. You can argue that the nature of surface is going to matter. That's where you get your traction from. It's known as a traction number or coefficient of friction. It's an experimental number. You can make that argument because you know that the carpet is going to give you more friction than ice, which means that the carpet generates more traction. And you can also argue that the weight matters. All right, so the weight is going to be related to the amount of force with which you're pressed up against the surface. So we will call it the apparent weight. So you can make these arguments. Or commonsensically, you can make these arguments, but where common sense fails is only 2 out of these 3 arguments are correct. All right, so the question is, which one do we get to abandon? Nature of surface is going to matter. Carpet still is going to generate more friction than ice. We got that. Different surfaces will give you different amounts of friction or traction. This is known as a coefficient of friction. This is your traction number. All right, so these numbers tell you about how much traction you will get from a surface. Weight does matter. The heavier objects will experience more friction. The size is not going to matter. All right, so the surface area contact is not going to be a contributing factor. So we just get rid of that. Nature of surface is going to matter. The apparent weight is going to matter. And this becomes a mathematical expression formula that tells you what friction is all about. All right, so traction is going to matter, and how much something appears the way is going to matter. How hardly something is pressed up by the surface. And that we will have 2 different frictions as it so happens. All right, and one friction is known as static friction. The other one is known as kinetic friction. All right, so one surface is at rest relative to the other one, then it's called static friction. All right, and then if one surface is sliding over the other one, it's known as the kinetic friction. All right, static friction is going to be larger than the kinetic friction. The maximum static friction is going to be larger than the kinetic friction. And you know this how. Whenever you're pushing up against something, it's going to take a lot more force to make something move than keeping it moving. That's how you know. And the reason why this happens is because the amount of traction generated when something is at the verge of sliding is going to be larger than the amount of friction traction object experience while it's sliding. All right, so for rubber on concrete, it's going to be 1.2 when the rubber is right at the verge of skidding. Then while it's skidding, notice that the traction goes back. Just move forward. All right, so whenever you lock up the brakes, it's going to be static frictional force at first. When the static frictional force is maximized, the vehicle goes into a skid, so it becomes kinetic friction at that point. Well, notice that only this portion of the static frictional force is larger than the kinetic friction. All right, so what the anti-lock brake system does, it just pumps the brakes within this region like 18 times per second, trying to increase the average static frictional force. All right, so as long as the average static frictional force is larger than the sliding or kinetic friction, this vehicle is going to come to a stop sooner. All right, so that's the meaning of it. All right, so the car versus an SUV traveling at 60 miles per hour, which one, if any, will come to a stop sooner? All right, so there's a bit of a problem here. I'm going to take you through the problem real fast. Not that you will have to do the math, but there's an interesting result that happens that we need to focus on. All right, so where we have the car, this is a mega truck. Boom, this one is 100 times heavier than this one is. All right, this is like 500,000 pounds. There's no such thing in real life. Then I'm setting these things up. So here's the mass, the weight, the normal force. Friction is going to be opposing the motion, force or friction. All right, so we'll figure out the weight, the normal force, the frictional force, the net force, acceleration, and blah, blah. The distance that it's going to skid, the time it takes for it to skid that distance. Here's the weight formula. You know, the car and truck is still going to weigh 100 times more. All right. Normal force is going to be the same as the apparent weight, the actual weight. And the normal force rating for the truck is going to be still 100 times more. Frictional force, opposing motion, these things are sliding, so the frictional force is going to be 17,000. This is still going to be 100 times larger than this one is, so it's going to be that 1,700,000. Net force is the same as the frictional force in opposing motion. All right, this is 17,000. This is 1,700,000. All right, so when you're looking at the acceleration of these both vehicles, notice that the accelerations are the same. Oh, all right, so the accelerations will be the same. Acceleration in this case is negative, so this is how fast they are coming to a stop. So what that means is both vehicles will take the same distance. They will skid the same distance and come to a stop, 140 feet, and they'll come to a stop at the same time. All right, so they will come to a stop at the same time. It's going to take about 3 seconds. You didn't expect that. That's counterintuitive. So the question is why? The reason why that happens is if you're driving in a 30-mile-per-hour zone at 60 miles per hour, if a kid runs in front of you, you will have to lock up your brakes. If you don't have an anti-lock brake system, as soon as you lock up the brakes, the car is going to go into a skid. So the skid marks is going to go all the way up to the kid, over the kid, and obviously it's going to be about 140 feet in line. When the police shows up, what are you going to say? You will say, hey, officer, I was going at 30 miles per hour. This kid came out of nowhere. I did the best. Look, I locked up the brakes, skid marks. all the way up to the kid, over the kid, 140 feet. All right, they will measure the skid marks. And then as soon as they measure the skid marks, they know you weren't going at 30, you were going at 60. That's it. Do they care that you're driving a Ford Tempo? Motorcycle, a truck, SUV, makes no difference. Why not? Because the friction is what brings you to a stop. And friction is proportional to weight. Vehicle twice as heavy is going to experience a frictional force twice as large. Vehicle 10 times heavier, it's going to experience a frictional force, which is going to be 10 times as large. All right, so it's proportional to weight. As a result, every vehicle will come to a stop within the same distance. That's what happens. The only thing that matters is the quality of the tires. Car versus a train, so which one comes to a stop sooner? You know which one is going to come to a stop sooner. It's the car, not because it's lighter or heavier. All right, because of the nature of surface. It's rubber on concrete, so it's going to be dry. All right, and then if the car is skidding, obviously this is the amount of traction that you end up getting from that surface. For the train, it's going to be dry, and if it's skidding, this is the amount of traction that's going to get from steel on steel. Rubber on concrete is going to generate more traction than steel on steel. All right, so the mystery of the guy on the 10th floor. He's got a broken neck because of the elevator accident, right? So he's on the 10th floor, the cable snaps. Safety system kicks in, got a broken neck. So the question is, how did he break his neck? All right, so here's an advanced storyboard before the animation takes place. All right, so the cable snaps, tongue is sticking out, stick is going up, goes up, hits the ceiling. What goes up must come down, either the first or the second impact. He's gonna break his neck, right? This is what most of you guys came up with in the beginning of the semester. All right, so when we do a simple experiment using an elevator, for example, what did we find out? As soon as the cable snaps, what happens? Nothing. You will feel weightless. That's it. That's the drama. You're inside the elevator, cable snaps, nothing happens, aside from the fact that you're feeling weightless. You cannot feel the floor under your feet. You will become suspended relative to your center of mass. You will be on the floor at all times. All right. You don't get to leave the floor because it's free fall. In free fall, everything falls at the same rate. Remember, Galileo said in a vacuum, everything accelerates at the same rate. So two objects, regardless of their weights, when dropped from the same height, will reach the ground at the same time. So what that means is the person in the elevator will be falling at the same rate. But you're thinking, hey, it's not a vacuum. What do you mean? You cannot ignore the effects of air friction. Oh, you can ignore the effects of air friction. Are you kidding? You're inside. You're shielded from the effects of air friction from outside. Elevator is the only one that's going to experience a little bit of air friction, but this thing is heavy. This thing weighs tons. This volume is relatively short. Air friction has no effect on this elevator. You and the elevator will fall at the same rate all the way down to the safety system. And then just before impact, boom, the safety system is going to engage and we'll bring you to a gentle stop. It's like the Tower of Terror if you're in Orlando or Six Flags, giant drop. It's exactly the same. No, you're not supposed to dive from it. And that's the extent of it. It brings you to a stop very gentle. So it's a gentle stop. Yeah, this person is a broken neck. So the question is, how? Is this scenario even remotely possible?
After their elevator plunged 40 stories. That story tops tonight's news briefs. Miraculously, the women suffered only minor injuries. One woman broke her ankle, the other broke her leg. After traveling down 6 floors, the elevator suddenly broke loose and began its free-fall descent. Authorities are investigating the cause of that accident in New York.
All right, so the answer to that question is yes, you can break bones inside of a falling elevator despite the safety system. So the question is how? Well, it depends on what you're doing inside a falling elevator. So if you were to find yourself in a falling elevator, what would you do? If you're caught in the middle, and all of a sudden you're thinking, oh, I'm feeling weightless. I want to balance myself. And you vaguely remember that there's a handlebar 2 steps in the backward direction. Let's walk. Can you walk inside a falling elevator? What do you suppose would happen if you did? How about jumping up from the floor? That's the one that I hear. When do you jump and how do you jump? I don't know. That becomes complicated. And what difference will that make? How about lying down on the floor? That's a favorite of high school teachers. Oh, you find yourself in a falling elevator. Boom. Spread eagle. Why? Because you can disperse the impact force until hydrogen surface area. That's going to reduce the pressure. One impact force. You cannot handle 2 Gs, 3 Gs. Not a big deal. All right. So the impact is going to happen 2, 3 Gs. It shouldn't be breaking your bones under the circumstances. All right. So what do? There isn't much that you can do inside a falling elevator is so happens. All right. So why not? The reason is you can't do too much inside a falling elevator is because you and the elevator are falling at the same rate.
Have only experienced a tiny slice.
So which means that
Time
you
and
will
space.
become suspended relative to your center of mass between you and the floor's face. All right, there's nothing you could do to close that gap if you're caught in the middle. There's nothing that you can push up against or whatever. You're suspended. You don't have a choice. All right. If you try to walk, what happens? Your body is going to do this. All right. And it's going to get out of alignment if you try to walk. There's no friction. You're not going anywhere. Like I said, without friction, you cannot walk. And there's no friction because you're up here to weigh nothing. You're not even touching the floor. That's what it means. Your body is just going to keep going out of alignment if you try to walk inside this element. All right. So you're suspended relative to your center of mass. You try to walk, and this is what happens. All right. So your body gets out of alignment. And then when you're doing this, when the elevator comes to stop, all right, your body's out of alignment, you will fall. There's no question about it. Can you jump from the floor? Yeah, you could probably push your feet against, extend your feet, and then just push up against the floor. And when you do that, it's going to give you a relative speed. So you will go up, hit the ceiling, and come back down. This would happen very gently. All right, so when you start to move inside a falling elevator, you start to take a chance because you are suspended relative to your center of mass. And when you start to move relative to your center of mass, your body gets out of alignment. Worst case scenario, you will lean forward and pull your legs in, and then it's going to give you a rotational speed in some direction. You could be upside down at some point. And then the safety system is going to kick in. And now it could potentially, obviously, snap your neck. The best thing to do is do absolutely nothing. Do absolutely nothing. All right. In the worst case scenario, you may end up wetting yourself, but that you can live with. All right. Do absolutely nothing. All right. So this is related to the mystery of falling cats. This is what happens. The bigger the distance is, the better the cats do. Meaning that the cat falling from the top of the stairs tower is going to do better than a cat falling from the second floor. That's what it means. So the question is, how is that possible? All right, it's related to air density. It's related to air friction. Air friction matters. This is not just free fall. This is in free fall. The only force you have to worry about is friction. The only force that you have to worry about is gravity. And now the air friction is going to matter. All right, this is a more realistic version of what takes place in real life. All right, so when something is falling, it's falling under the influence of gravity. Gravity is what gives you a weight. And because you start to move, you're going to start to experience air friction. All right, so the air friction is going to be dependent upon a number of factors. Air density is going to matter. Exposed surface area is going to matter. Your speed is going to matter. And what else? And also the conditions of the air mass is going to matter. So this represents the conditions of the air mass. All right, so we put them together back to the air friction. All right, so I'm just going to pull forward and get to the final equation. All right, so what matters is in terms of how fast you're falling, the effects of air friction is going to be such that at some point this frictional force is going to get larger and larger because you're speeding up, and it will become equal to your own body weight. So under the circumstances, the net force acting on you is going to be 0. You're still falling, but you're falling at a constant speed, so you're not going to have any acceleration at that point. Now, the speed with which you're falling is known as your terminal velocity. So once you reach your terminal velocity, you stop accelerating, so that's what it means. And then I'm looking for an expression for the terminal velocity right now, mathematical expression. So notice that your terminal velocity is going to depend on your weight. So it's going to be directly proportional to your weight, and it's going to be inversely proportional to the exposed surface area, right? So for an average sized human being, the terminal velocity is about 120 miles per hour. Obviously, the weight is going to matter. So for something lighter, it's going to be much less. For something heavier, it's going to be much more. The other thing that's going to matter is the exposed surface area. All right, so for an average sized human being, it's 120 miles per hour. But if you have a parachute, it's no longer 120 miles per hour. It's going to be between 15 to 20 miles per hour. All right, so larger the exposed surface area is, smaller the terminal velocity.
One day,
So what's
8
the
lives to
cat?
go. You wouldn't
That's the
believe
case.
a tough kitty in Boston just survived.
Can't believe this, right? Sugar the cat is still purring and walking unbelievably after falling 19 stories from the window of a Boston apartment building. Amazingly, no broken bones, no cuts, just some minor bruising on her lungs. Sugar's owner cracked the window so Sugar could cool off while she went to work. She says there's no other way the cat could have ended up on the street.
And experts say cats can survive dramatic falls by splaying their legs pretty much like a flying squirrel.
So they kind of fly and breaks their...
Have you ever seen like the really slow motion video?
Yeah.
They wheel their bodies. I'm starting to act like a cat. I'll stop. But it's pretty amazing.
So if we ever come across that situation, we'll just...
Splay.
Well, there we go. Splay, everybody.
All right, so it's been discovered that if the distance of fall is more than 70 feet, the cats will do better. If it's less, they will do worse. All right, either way, the cats will be fine, but the question is why. All right, so here's a cat falling from the top of the stairs tower. So what's going to happen is the cat is going to accelerate under the influence of gravity and then elevate up to its terminal velocity. Cats don't weigh that much, 6 to 12, 14 pounds. Their terminal velocities will be anywhere between, I don't know, 45 to 60 miles per hour. That's what you're looking at. And then they will open up their surface areas, and then they get this 45 mile per hour terminal velocity, and they will hit the ground at 45 to 60 is what I'm looking at. All right. Here's a cat falling from the 5th floor of a building. This cat is going to hit the ground around 35 miles per hour. All right. So this cat will still do better than this cat. So the question is why? Why is it that this cat does better than the other cat? This cat is still moving faster, and this cat is falling a longer distance. All right, what's the reason for it? A lot of you guys mistakenly think that, oh, this guy's gonna have plenty of time to actually adjust his body and land on 4 feet. Guys, that's complete nonsense. How much of a distance do you think that a cat needs in order to turn around and land on 4 feet? All right, even less than a foot. In either scenario, the cats have plenty of time to break themselves up. So it's not like a big deal. All right. So what's the difference between this cat and that cat? Well, this cat is falling at its terminal velocity. This cat is still accelerating. This cat is falling at its terminal velocity. There's no acceleration here. If you're falling at your terminal velocity, the muscles are relaxed. If your muscles are tense, that shortens the impact time. Impact time goes down, acceleration goes up. And acceleration is what kills you, what maims you, what breaks your bones.
Spring and agility. Their ability to avoid injuring themselves when they fall. By using their righting reflex, their valuable knack of automatically turning in the air and landing safely on path. Spring and agility.
Regardless, short distance or long distance falls, cats tend to do fine either way, except they tend to hurt themselves more. Injuries tend to be more severe if it's less than 70 feet. All right. The reason why the cats will do fine because they're much better at absorbing impact. Translated physics, they're much better at increasing the impact time and reducing the acceleration. All right. So with the extra muscles that they got in their shoulders and hind legs, they can increase the impact time. That's what it is. All right, so this is what you see most of the time in real life. Here's a cat jumping from a high rise. And you know, this is not the first time this cat is doing it. Neither is it the second time. More than likely, this is how this cat gets out on a daily basis. All right, so it's more than 70 feet. And then this person decided to capture it in video. Somehow, instead of stopping the cat from jumping, and then the cat jumps. All right, it's not a big deal, perfect landing. And there's its friend, and then they start playing chase, and that's it.